Okay. Okay, it's my pleasure to introduce Ole Warnaar, and he tell us about a conjecture in need of a Baxter.
Thanks very much, Vladimir, and hello everyone. It's a pleasure to speak at this very special occasion. Of course, a somewhat sad occasion, but anyway, it's great to be part of the celebration of Baxter's work and life. Um, I'm, s- I think Murray already mentioned that a moment ago. I'm one of a rather large contingent of Dutch people who are here now in Australia, probably primarily because of Baxter and also, of course, because of the people around Rodney, people like Paul Pierce and Murray Batchelor, Vladimir himself, Tony Goodman, and various others, Peter Forrester, and so on. Um, Certainly for me personally, that is, I think, why I'm in this country, even though I've drifted away from mathematical physics. Um, Hopefully, I can still tell a story today that is reasonably related to Baxter's work and is perhaps a testament of his influence across many areas, not just of statistical mechanics, but also pure mathematics and I'm sure beyond. Um, my personal interactions with Baxter, there have been many over the years. I first came to the ANU when I was still a PhD student. And in the Netherlands at the time, any student, I think, in science and could, without much administration involved, apply with Shell for a travel grant to go anywhere of your choosing. And so for me, that was going to Canberra and visit Rodney and the group around him. So that was quite fantastic. And then, of course, over the years, I've met him many, many times. I think most recently, my interaction with him was when I was the president of the Australian Mathematical Society, and Rodney contacted the OSTEMS and also ANZAMP, as part of OSTEMS, to establish what is now the Rodney Baxter Prize in mathematical physics. So it was, of course, very generous of Rodney to set up this prize with significant funds involved. And so I think his legacy will definitely live on. Okay, so maybe to my talk on a conjecture in need of a Baxter, and that's, I think, very, very true. Let me see if I can. Before I start my talk, this is, well, most of the work I'm not going to describe today because it's probably, I don't have enough time and it's also a little bit too technical and too much in the area of pure mathematics. But so I'll only give you a glimpse of what we've been doing. And these are three of my collaborators. They're all pure mathematicians, although they're all sort of in again, the school of pure mathematics that I think is heavily influenced by Rodney Baxter. In particular, I know there's some Japanese people in the audience. Shunsuke, for example, is a former student of Kashiwara, who of course recently was awarded the Abel Prize. And in some sense, Kashiwara's work on crystal base theory, you could argue that this is sort of the mathematical formulation of Rodney's ideas around corner transfer matrices, which is something I'll bring up a little bit later in my talk. So, okay, so it was already mentioned, I think it was Shi Wen, the Rodney's work on the hard hexagon model. And so if you Google this, then there's a whole Wikipedia page, well, more than one page, it's I think 4 pages long, describing some of Rodney's work on the hard hexagon model, which he did in the 1980s. And this was a reasonably influential, well, more than reasonably influential, a very influential paper. And in particular, what it did, it connected some of the statistical mechanical models with the world of Q-series and partition theory. And that's very much what my talk is going to be about. So what was the hard hexagon model for? I'm sure most people are familiar with it. so this is, we take a triangular lattice and we put these hexagonal particles on the lattice, and so they can move around, but they cannot overlap. I've colored some of these particles here. The particles actually do not carry a color. I've simply colored the particles because on this triangular lattice, there are 3 sublattices. And so what I've done is, this will be relevant in a moment, if a particle is centered at one of the sublattice colored blue, I've just made the particle blue. But of course, when it moves around on this lattice, it will constantly change its color, because if it moves one position to the left, for example, a blue particle will become a green particle and so on. So the particles themselves don't have color, it just indicates on which sublattice they reside. Okay, so that was the model. So just these hard hexagons moving around. And what Baxter did, well, he computed various quantities for this model. And of course, he did this in the Baxter way. So he did this exactly, but not rigorously. So Jacques Perk was already making reference to this. And in particular, he computed the partition function for this model. So as a pure mathematician, you can just view this as computing the generating function of configurations of hard hexagons on a lattice. And so the capital N is just the size of the lattice, and I'm not going to specify exactly what the geometry of the lattice is, because that's not really going to play a role, and we eventually take the size of the lattice to infinity. But you can imagine that there's some finite lattice, and you count a number of configurations of these particles, and then you compute its generating function. And so that's what he did, and then he raised this to the power 1 on n and took the limit when capital N goes to infinity. And what he found is that, maybe not that surprising, but that there's 2 phases. So there's this low density phase where basically the particles, they're free to move around. And so each of the 3 sublattices, they're occupied by roughly the same number of particles. So in other words, the sublattice densities, they're going to be the same. But then at high density, the exclusion that these particles, that really starts to become important. If you want to have high density, so if we go back to the picture here, then of course the particles will prefer to all reside on one of the 3 sublattices. And so this leads to a phase transition between a phase where all 3 sublattices are equally favored and to a phase where one of the 3 sublattices is chosen and most of the particles sit on that lattice. That of course will allow you to sort of pack them as closely as possible. And Baxter, for example, he found the exact value of the critical point. And this is the first sort of hint at something Rogers-Ramanujan or Q-series type is going on, because you see these 5s showing up here. So what more did he do? So he determined essentially, well, he tried to compute the probability that a particle will reside at one of the 3 sublattices. And for this, he used his famous corner transfer matrix method, which I already mentioned earlier. And this led him to the computation of what we are now know as one-dimensional configuration sums. And this is the one-dimensional configuration sum that he needed to compute. So it's a function, and as input, we can only have either the sigma 0 is sort of the central side of the lattice. So it can either be occupied or it can be empty. So it can either be a 0 or a 1. So 0 means that the side is occupied, and a 1 means that the side is, yes, I should say a 0 means that the particle is there's no particle, and a 1 means that there is a particle. And then, of course, there's some conditions, and in particular, the fact that the particles cannot overlap is indicated by the fact that if you take a sigma I and a sigma I plus 1, so you look at essentially a one-dimensional path on a lattice like this, and then obviously if a side is occupied, so if this side is occupied, oops, I'm trying to, okay, so if a side is occupied, then of course the side next to it cannot be occupied to avoid the particles overlapping. So that's expressed here in this sum. And what Rodney observed is that these f's of 0 and f of 1, they have a very nice closed form expression. He first observed this just using computer experiments, and then later, of course, he actually obtained these expressions, but he found that you get these very nice infinite products. And these are the famous infinite products related to the Rogers-Ramanujan identities. So that's how he discovered the occurrence of these identities in this hard hexagon model. Okay. So, of course, now we know that this is not so much a surprise. I mean, at the time, I think it certainly was, because we understand that these one-dimensional configuration sums, really what they're doing, they're computing characters of irreducible representations of the Fourier-Soro algebra, and that's really the what's describing, I guess, the scaling limit of this model at criticality. And in particular, this model, it's non-unitary, and so it's described by non-unitary minimal model corresponding to 2,5 in this classification of minimal models of conformal field theory. And so that in this case, there's two irreducible representations, and the characters of these representations precisely correspond to these nice infinite products that you see, these nice Rogers-Ramanujan infinite products. Okay. So I want to move on to a more general partition problem, and that's Gordon's partition theorem. So this is a result from the 1960s, so predates Rodney's work by about 20 years. And it's a generalization of the Rogers-Ramanujan identities. I haven't really told you what the Rogers-Ramanujan identities are, but they're included here in Gordon's partition theorem. So we're considering an integer partition, so that's just a weakly decreasing sequence of non-negative integers, such that there's only finitely many terms in your sequence. And then, of course, the sum of the terms, that's the number you're partitioning. And so here, my example, I have 5, 3, 3, 2, 2, 2, and 1. So that's my example partition. And a convenient way to represent the partition is using its Ferris diagram. So just a bunch of dots where the first row indicates the largest part, the second row indicates the second part of the partition, and so on. And what I've done here to the left of that Ferris diagram, I've indicated the frequency or multiplicity of each part. So there's one part of size 5, there's two parts of size 3, there's 3 parts of size 2, and then there's one part of size 1. And so these FIs, they very much play the role of Baxter's sigma I. So Baxter had only sigma could be 0 or 1, and that gave these Rogers-Ramanujan partitions. So what does that mean? That means that, well, if a part occurs, for example, if you have a part equal to 5, it can only occur once, because Baxter only allowed the sigma to be 0 or 1, so you can't have any multiplicities higher than 1. But it also says if sigma I times sigma I plus 1 must be equal to 0, that means if you have a part of size 5, for example, you can't also have a part of size 6 or 4. So consecutive part sizes are not allowed. Okay. So this notion was generalized by Gordon, where he said if you take a frequency of a part of size I and the frequency of a part of size I plus 1, this must be less than or equal to some integer k. And that must be true for all part sizes. And then moreover, he says that the part size of size 1, it can occur with multiplicity at most a, where a is some integer that is bounded by k. And so if you set k is equal to 1 here, then you get fi plus 1 is less than or equal to 1. And so that's exactly the same as if you replace your f's by sigmas, that's the same as saying sigma I times sigma I plus 1 is 0. So that's the hard hexagon case. And so this is simply a generalization of the conditions that Rodney encountered in his solution. And then Gordon's theorem says that if you compute a generating function, so in Rodney's language, this would just be the one-dimensional configuration sum of some more complicated statistical mechanical model, perhaps, that again you get a nice infinite product. But previously we had a modulus 5, as you can see here in the Rogers-Ramanujan identities, and now the modulus is actually 2k plus 3. So again, if you take k is equal to 1, you simply get back those earlier two products. There's two choices for A in this case. A is 0 or A is 1, and that gives you exactly these two one-dimensional configuration sums of Rodney. So that's Gordon's partition theorem. And in fact, this also arises in the context of solvable lattice models. So rather than the hard hexagon model, you need a generalization thereof, and that's what's known these days as the Forrester-Baxter model. So that's a generalization of the Andrews-Baxter and Forrester model that's perhaps better known. So this is sort of the generalization where the Boltzmann weights are not necessarily positive, so it gives you non-unitary conformal field theories. And instead of looking at the minimal model 2,5, if you look at 2,2k plus 3, this exactly gives you these Gordon partitions. So these Gordon partitions and this Gordon partition theorem also arises in the context of solvable lattice models, and the sum on the left, again, you can interpret this as a one-dimensional configuration sum for some solvable lattice model. Okay. All right, so now I'm going to do something that may appear somewhat unnatural and perhaps a little bit of overkill given how simple the model is. But given a partition, so one of these Gordon, well, or general partition, but you can think of a Gordon partition, I have these frequencies, so that tells you how many times a given part occurs in that partition. And what I can do is I can arrange these frequencies in this sort of zigzag shape, as I've shown here on my slide. And moreover, what I'm going to do, these numbers A and K in Gordon's partitions, I'm just going to put them as sort of boundary conditions on the left. So there's an A in the top row, and then in the row below it, I have K minus A. And so for my previous example of the partition 5, 3, 3, 2, 2, 2, and 1, so this would be the configuration of numbers. So this 3 here, for example, that you can see here, that indicates that I have 3 2s. And this 2 here indicates that I have 2 3s and so on. Okay, and I also indicate, I make a choice for A and K, so maybe 1 and 5, and that gives me these numbers here at the boundary. And then Gordon's condition that Fi plus Fi plus 1 is less than or equal to K, which in the above example, K is 5, means that any path, and again, path is an overkill in this particular example, but later I'm going to generalize this and it will make more sense. So a path is simply a two-step walk starting at the bottom and going to the top. But you can only jump to an adjacent side. So that for any path from the bottom to the top, that the sum of the numbers, so for example, I could do a path from 3 to 2, that the sum of these numbers should be less than or equal to the sum of the numbers here on the boundary. Okay, so that's a different way of encoding Gordon's partition theorem, or Gordon's partitions, in terms of these little zigzag configurations of frequencies. So here, again, is an example to check that this is an admissible configuration. Obviously, if I sum the two boundary numbers, well, they always will sum up to K, so that's never going to exceed K just by construction. And then I get 4 plus 1, again, that's equal to 5. That's okay. Here the sum is equal to 4. And you can run through all of this and you'll never exceed 5. So this is an okay partition. All right. So now a big jump in time. So that was Gordon. That was 1961. And then a few years ago, a number of quite famous representation theorists came up with a generalization of Gordon's partitions. And I'm going to explain to you, or try to explain to you what they did. So now we are still looking at integer partitions, but now each part can be colored with, in general, n different colors. So as a sort of to give you an example, I've chosen 3 colors, red, blue, and green. And so here's the same partition I had before, 5, 3, 3, 2, 2, 2, and 1, but now each part is given a color. Other than that, nothing changes. And so again, I can keep track of the frequencies, but now the frequencies carry an additional color label. So for example, I have an F5 that indicates, well, which parts of size 5, but it could be a blue 5, or it could be a red 5, or it could be a green 5. So these frequencies, they have an extra label that indicates the color. Here, I haven't added that label. Here, I've just used an actual color, blue, red, and green. That's much easier to look at in this talk. So again, we have these frequencies, but now they're colored frequencies. And what are we going to do? We do exactly as before. We place these frequencies in a zigzag pattern on a lattice. So the first, again, there's some boundary conditions. So previously we had, so sorry for jumping back, we had A and K minus A from Gordon's theorem. And now I have 4 points on the boundary. Well, the boundary is a little bit oddly shaped. So you see K3, K2, K1, and then a K0. And so these 2 leftmost columns, you should think of them as being the boundary. And then the first proper color, it has the F1s, then the F2s, and so on. And again, the zigzags up and down. And given such a partition, you place the corresponding numbers on this pattern, this frequency array. And CMPP say that, well, to get a valid partition, what you want is that if you again take all of the paths from the bottom to the top, where again, if you take a path, you can only go to a neighboring vertex on this graph here. If you take such a path, the sum of the frequencies along a path should always be less than or equal to the sum of the numbers here that you have on the boundary. So again, the boundary condition you can think of as fixed, and then you need to check for every possible path. So now the combinatorics is much more complicated than it was in Gordon's case. And so that's what they did. So here's an example. So the same partition as before, 5, 3, 3, 2, 2, 2, and 1, but again, the parts are colored. And so this would be the corresponding frequency array. I made some choices for these boundary variables. So 1, 2, 3, and 0. So that's what you see in these first 2 columns. And then I put all the correct numbers, or hopefully I did this correctly, corresponding to this partition on this lattice. And it should be the case that whenever you take any path you try, so maybe 1, 1, 2, 0, 1, 1, the sum of these numbers should be less than 6, less than or equal to 6. Okay, and so what was the conjecture? The conjecture was that the generating function of these colored partitions satisfying these really complicated conditions that are encoded by all possible paths. So there's a lot you need to check, but if you do, then you find that this is once again a nice infinite product. And this time the modulus is 2k plus 2n plus 1. So in the Rogers-Ramanujan case, we had the modulus was 5, and then we went to Gordon, the modulus was 2k plus 3, but now this 3 is being changed to 2n plus 1, where n is the number of colors. So this was their conjecture. They didn't actually say what this product should be. They couldn't quite work out what it was. And but they gave some recursive procedure that if you fix your choice of boundary variables, so now there's n+1 of them, if you fix those, then your computer can just run an algorithm and it will tell you what this infinite product should be. Okay, so that was their conjecture. And so the first question, of course, they had is, well, what is actually this infinite product? Can we find this explicitly? And then they also said that there was a real surprise to them. They were representation theorists, but they said these products didn't appear to be related to any representation theory. And so unlike the Gordon case, where we know this is related to the Virasoro algebra. Okay, well, in fact, they made no reference to the Virasoro algebra. Instead, they made reference to another type of representation of affine SL2 to principal characters of certain representations known as standard modules or integrable highest weight representations. It's not important if you know exactly what they are. The characters of these are the same as the characters of the Virasoro algebra. That's all that matters. So this is just a different way of understanding Gordon's theorem from the representation from a representation theoretic point of view. But as I said, they really said it didn't seem to extend to the n-color case. Well, the first thing we did is we actually did find the closed form expression. So this looks very, very complicated, and I don't think the details are so important. But the point is that the product can be expressed in terms of Jacobi theta functions, and Nalini already told us about the importance of elliptic functions, and of course the building blocks of elliptic functions are these Jacobi theta functions. So this is a very nice modular type of expression. That's all that matters, and it's very explicit. So that's one thing. Of course, that's once you have found this, you can certainly check that this recursive procedure that CMPP had proposed indeed is solved by this complicated looking product over Jacobi theta functions. But the great thing about having an explicit form is that it's a little bit easier to recognize whether this is something known or not known from representation theory. And it turns out, and this is sort of one of these big coincidences, because this product had arisen before in representation theory, and the lucky thing was that that appeared in my own work. So for me, it was fairly easy to recognize it, and which I'll try to describe now what's going on. So rather than affine SL2, we actually have to look at this type A, but now A even and then twisted. So there's this 2 here as an upper index. So it's a slightly more complicated affine Lie algebra, and here's its Dinkin diagram. And again, you can compute the characters of the standard modules for this thing. I've given here what the definition of that character is, but it's not so important. But these characters you can explicitly compute. And remember what I said earlier, that instead of interpreting the product in Gordon's theorem as characters of the Virasoro algebra, you could also interpret them as principal characters of affine SL2. And principal character really means that you're not looking at the full character, but the character is expressed in these formal exponentials of all of the simple roots of the affine Lie algebra. And what you do is you replace all of these formal exponentials by Q. So now you get a formal power series in just a single variable, and that's exactly the Q of the Q series, or the Q of Baxter's expression for the one-dimensional configuration sums. But it turns out that you need to do something slightly different here, because instead of taking the principal character, you have to do something slightly strange. One of these formal exponentials, you replace it by -1. So that's a non-standard thing to do, and it's, for example, not described in Katz's book on affine Lie algebras. So we know that if you do principal specialization, you always get a nice infinite product. But it turns out that if you do some other non-standard specializations, you can also get infinite products. And that's precisely what you get in these CMPP partitions. And so this infinite product had arisen in a different context in work that I'd done with Michael Griffin and Ken Ono on number theory. So it was a real coincidence that when we started looking at these CMPP partitions, that it turned out we got exactly the same infinite product showing up. Okay, so that's nice. So now, of course, we can give a representation theoretic form of the conjecture, which essentially says that the generating function of these CMPP partitions is given by this, well, not quite principal character of twisted type A, but something that's very close to it, one of these non-standard specializations. Okay.
We don't have much time left.
Yes, I'm at my last slide. Unfortunately, it turns out that trying to prove this conjecture appears to be unbelievably difficult. So the conjecture is now 3 years old and no one's made any progress whatsoever. And really what appears to be the problem is that we don't yet have a candidate solvable lattice model whose one-dimensional configuration sums are described by these partitions. And why would that help? Because, I mean, I've been sort of glossing over the details, but these one-dimensional configuration sums, they usually are not infinite sums, but you take finite. So you first work on if you wish, on a finite number of variables, and then you take the limit when the system goes to infinity. And if you look at these finite systems, they satisfy really nice recursions, which can help you solve the system. That's exactly what Rodney did in his work, what Andrews, Baxter, and Forrester did in their work, and so on. But here we don't yet know what the underlying solvable lattice model is, so we don't know how to finitize this system and get recursions that would describe these partitions. And so what we really need is someone who tells us what the correct lattice model is, so that we can hopefully make at least some progress in trying to settle this conjecture. So thanks very much.
Paul,
Although, of course, I know Baxter, but let me make a curious comment. The hard hexagon model is actually Z3 parafermions. It has a Z3 symmetry, and consequently, it has the same central charge as the three-state quads. So the central charge is 4/5, but the central charge you're seeing in the expressions for the one-dimensional configurational sums are minus 22 and 5. That's Li Yang, but they satisfy the same functional equations. So I'm wondering if the reason you can't find the right lattice model here is because you're looking for the wrong central charge.
Ah, well. Because, yeah, even for this more general model, right, I've only shown you the central charge for this 2K plus 3, but if we go to this twisted type, are we looking at the wrong central charge?
Yeah, I think the first thing you need to do is understand what is the relation between those two central charges. I mean, I'm really shocked that you see the minus 22 on 5 in the one-dimensional configurational sums, because for Virasoro characters, the degeneracies of your characters will tell you what the effective central charge is. You just have to extrapolate a simple sequence.
Nonetheless, if I were to give you this central charge and I were to give you just the Gordon case, it's not hard to identify that that's Forrester Baxter. It's not that we need to work with some effective central charge rather than the actual one. I mean, it immediately just pops out. So I'm not sure the reason is because we're looking at the wrong central charge. We need probably some. Yeah, I don't know. It's a good suggestion, but I'm not sure that's the biggest problem here.
Yeah,
But maybe. Yeah.
This, but
okay, any more questions? Yeah, I have a question myself. Did you or someone else try to write down the configuration sum for three-dimensional lattice?
So that's not related to one. I don't think so. I mean, this comes from corner transfer matrices. Has anyone ever done this for 3 dimensions? Maybe Ian Enting numerically, if that's possible, but I mean, what's a three-dimensional corner transfer matrix? It would, right?
You divide the space to 8 nice corners.
Yeah, I don't believe you should know better than I do because, as I said, I haven't worked on solvable lattice models for a little while, but I don't believe so.
Okay. Well, let's thank the speaker again.